Section 7 involves what we call optimization. And in Algebra 2, you guys did optimization type problems. If you remember the feasible region stuff, where you had the objective function and all that, you had to graph and with inequalities and make your constraints and stuff. Very similar idea going on, except we're not doing that here. We are building functions that describe the situation, and then we're going to be winding up taking derivatives to find our maximum and minimum values. So that kind of has been leading up in this chapter to this point. Obviously, we've been taking derivatives to find maximum and minimum values. So here we are here. Now we're applying it. So calculus is very useful for this. Problems that ask you to find the greatest profit, least material, least time, longest distance, largest volume, least size, anything like that, you can actually use calculus to solve. Have you ever seen the problem that asks you to do this? It's always on the map test. It's always on the ACT. And I actually had you guys do this in Algebra 2. There was a day where we took a square piece of paper and cut corners out of it to try to make the box of maximum volume. And the people who were most successful sat there and plugged in numbers. They were figuring out how much they were cutting out, and then figuring out the dimensions of the box they were creating, and then they were plugging numbers in to figure out which volume would give them, or which result would give them the most volume. There's an algebraic way to do it, and there's also a calculus way to do it. The calculus way to do it gives you the answer much more accurately than any other method. That's how I figured it out. Yep. And that's going to be the first problem that we do once we get done with how to do every optimization problem. So first of all, you're going to identify what you're given and what you're supposed to find. Just like any story problem, that's what you're supposed to do, right? But on these, you're also going to need to draw a picture. The picture, a lot of times, will help you figure out what it is that you're supposed to be doing. Then for number 2 and 3, I have identify the primary equation and any secondary equations. The primary equation is involving whatever it is that you're trying to optimize. So if you're trying to produce a maximum volume like in that box problem, then you're probably going to be working with some sort of volume function. Maybe length times width times height. Okay, that's the primary function, or that's the primary equation. The problem with V equals length times width times height is there's actually like 4 variables there. Because length can change, width can change, and height can change. And that's why we come up with the secondary equations. We want to get this primary equation down to where there's just one single independent variable. And you do that by using secondary equations. And then you'll substitute in, you'll do some substitution with these secondary equations up here until you get it down to like V equals just some expression in terms of the length or something like that. Once you have that situation taken care of, then number 4, identify the feasible domain. You want to talk about what values. So like if this was a function just in terms of the length, then what values can my length be? Where, like obviously length you can't have negative, so you'd probably start at 0 length, and then how far can I go with my length? That's what the feasible domain is. Values of your variable that make sense for the problem. Nothing outside of that domain works. What that winds up being is like the endpoints of your interval. And now when we're trying to find an absolute maximum or an absolute minimum, we differentiate our equation, and then we look within that interval, including the endpoints, to figure out where that maximum or minimum or whatever it is that we're looking for is. Check your endpoints of your feasible domain and any critical numbers in the domain. One of them will be your answer. And then you just put your answer back into the context of the problem. So right away, let's talk about this maximum volume of an open top box. Now there's important information here. We want to design an open box with a square base. Very important information. And a surface area of 108 square inches. Also very important surface area. Or surface area is very important. But Then it says what dimensions will produce a box of maximum volume. So that maximum volume tells me that I need to make my primary equation, the volume equation, for a rectangular prism, basically. Okay? All right. So the volume equation for that situation is V equals length times width times height. That's my primary equation right there. Now I need to start trying to figure out how to get this thing down to one variable. So it'll be volume equals something with just one variable, all right? We do have surface area, but hang on. Let's take a look at the picture. Notice I've drawn a picture here. Always draw a picture. And I'm going to use this idea of a square base. No.
Oh, no. I guess the size.
Right. So the length and the width are the same then because it's a square base, okay? Now I can call that whatever I want, but I'm going to call it x. Yeah, so then the base is just x squared, okay? Now I don't have the height in terms of x. They didn't give me any of that information, so I'm just going to call that height. So now at this point my primary equation becomes x times h, which is just x squared h. So now there's only two variables that we have here. We want to probably get rid of this h somehow. Okay? The way that we get rid of that h is they tell us the surface area has to be 108 square inches. So now if I calculate the surface area of this thing, it's an open top box, so there is no lid, and I set it equal to 108, there's going to be an h involved and there's going to be x's involved. So then I can solve for h, and then whatever I get from that, substitute it in here, simplify it down, and then I'm ready to go. Okay? So let's talk about surface area. How can I calculate the surface area of that open top box? How do you calculate surface area? Well, let's just say, how do we calculate surface area first? So you find the area of all of the sides, all right? So surface area is 108, and that's going to equal the area of all of the sides. Well, I have a base, and then I have 1, 2, 3, 4 sides. What's the area of the base? X squared. And then I'm going to add on the area of all the sides, which is x times h for each one of these sides, but there's 4 of them, so it's going to be plus 4xh. There's your surface area, and now we can just solve for h. So to do that, I subtract, so I have 108 minus x squared equals 4xh, and then divide everything by 4, and then I'm going to rearrange the way this is written. H equals 108 minus x squared, and we're dividing both sides by that 4x. So that's what h is in terms of x. And so now I can take that and substitute it in right there for that h. So I get v equals x squared times 108 minus x squared over 4x. Distribute, or you could say that this x squared and this x goes away. So I'm just going to distribute first just to show you. 108 x squared minus x to the 4th over 4x. So when we simplify that, v equals, we can split this into two separate things. 108 divided by 4. 25 would be 100, so 27. X, right? Minus x to the 3rd over 4. So there's our volume function in terms of our one independent variable, x. So that's ready to go. Now the next step that we came up with was identify the feasible domain so that we can have the range of values that we're looking at. So the feasible domain, we're talking about x. That's our independent variable. So x has to be between what two numbers? 0 for sure, because this is a length. No, not infinity. It's not 27 either. But you're getting closer. It's not 108. Can x be 108? No, why not? Remember, this is a square base, right? We do have 108 square inches available. So if the height goes to 0, then all of that 108 square inches goes towards the base. Agreed? If 108 square inches goes towards the base and the side lengths are both x, then the length of x would be the square root of 108. Make sense? Okay. So then we can simplify that 108. There is a perfect square that goes into that. 36. 36 times 3. The square root of 36 is 6. So 6 root 3 is the feasible domain. Okay? So we're checking now between 0 and 6 square roots of 3 using this function right here. So we are ready to go. We can find the derivative of this because the derivative of this will give me, if I set it equal to 0, my critical numbers. And from my critical numbers, I can determine where the maximum or minimum value is. Okay? So take the derivative. We get v prime equals 27 minus 3/4 x squared. Now I'm looking for critical numbers, so I'm going to set it equals 0, good. And I have 27 equals positive 3/4 x squared. Multiply both sides by 4/3. So I'd have 27 divided by 3, which is 9. 9 times 4, which is 36. Equals x squared. So therefore, x equals plus or minus 6, but we can't have a negative. So x equals 6, and we're dealing with inches. Okay? So now I just need to check the endpoints of my interval here, 0 and 6 root 3, and then also the critical number that I just found, 6. Take 0, plug it into my volume function. I get 0, obviously. If x is 0, then there is no dimension to this box. So we get 0. It's not going to be that. If I take 6 root 3 and I plug it in to my volume function, basically, in order to get 6 root 3, the height has to be 0. And then is there any volume to this thing? No. So I get 0 there as well. So now I'm up to 6. Take 6 and plug it in here. 27 times 6. Bunch of mumbling. It's not 62. 6 times 7 is... Is it 162? Okay. So we have 162 here, and then 6 cubed. 36 times 6. Thank you. Divided by 4. So we have 162 minus 54, which is 108. 108 inches cubed there. So there's your maximum volume right there. Okay? When x is 6. So x equals 6. What dimensions will produce a box of maximum volume? So x equals 6 inches produces this box of maximum volume. So we need a length of 6, a width of 6, and a height of... Take the 6 and plug it back in over here. We have 108 minus 36. That's probably like 72. And then 4 times 6 is 24. 72 divided by 24 is just about 3. So these are all inches. That's how you do this problem. That's how you do problems like this. Draw a picture. come up with your primary function, figure out how to get down to just one independent variable in your primary function using these. You might have more than one secondary equation. Figure out your domain, your feasible domain. Once you have this guy down to just one variable, it's fairly easy to do. And then from there, you have this situation here. Get your critical numbers, find your maximum or minimum or whatever it is that you're looking for. Okay? One thing I want to point out is this right here. The graph of this would be a what? It's a parabola that opens which way? Down, because of that negative on the x squared. Okay? So if I have a parabola that opens down, it makes sense to have a maximum value. Okay?